All right, here we go. All right, first off, wonder why I'm wearing a soccer jersey today? These people from Period 3, I'm giving you a shout out. They always wear soccer jerseys. I don't understand why. They have, they fly Emirates. I don't even get what these jerseys mean. There's a Real Madrid. I don't know what a Real Madrid is. Is there a fake Madrid? I don't get these teams. I don't understand soccer. I like American football. But anyway, I always make fun because they always wear their last name on the back of these like Philadelphia Union jerseys. I'm like, this one kid, he's like, I said I didn't realize he played for the Philadelphia Union. It's like a violation, It's like if you get an Eagles jersey with your last name on it, that's a violation. You don't play for the Eagles, okay? It's like me getting a Pitt jersey with my name. I never played for Pitt, all right? That's just a violation. So again, they got me this jersey. So mad shout out to these people right here. I'll put your picture up here, but not too close. We can't see you on here. Thank you there, all the best. iVizzle, J Sizzle, IV. The only kid I ever taught it, always puts a Roman numeral at the end of his last name. It's good, mad respect to his family. You got the boy twin. I call him Boy by his last name, but his sister's in the same class. Shout out to that family. Very good. Hizang, who plays for the Philadelphia Union, supposedly. He wears his Philadelphia Union jersey with his name on the back of it every day. And then we got the Deuce, Kern Dog. And give Kern Dog credit, he's the one that came up with the brilliant, well, doesn't like atomic number define the element, define what it is? Brilliant. So thank you, you soccer nerdy crew, man. You guys got some issues, but it's all good. That's why we get along so well, except for the soccer. All right, well, thank you very much. You will be remembered fondly. All right, here we go. So, in class, this is more for this, for Futures Challenge Science, but again, this will help you guys. I know we started doing bond energy calculations this year. I saw that on this year's test for the first time. I saw it was a bit of a weakness. Maybe we ran out of time, maybe we needed more practice with it. So of course now here in June, like we tell you, when you work hard in the class, you're expected to finish strong. So it's here in June on a Friday afternoon, we're still making videos. Why? Because if you're supposed to finish strong, so am I. All right, so again, we only have a little bit of time left. You're expected to finish strong, you current people this year. So anyway, you've learned in class that, through the curve, to start a chemical reaction, a chemical change, to make something new, you got to break chemical bonds. But inside those chemical bonds are stored energy. And every type of bond, given the type of molecule, given the combination, has a different amount of stored potential energy in it. And it requires heat to break that bond. We talked about activation energy. We talked about the effect of a catalyst. So we learned that when bonds break in chemical reaction, energy has to be added into the system, the endothermic part of the reaction, that process. And then we hit that peak, that transition state where all of a sudden now things are broken apart, mass chaos. They start to figure out, well, who goes with who? We talked about who goes with who when we predicted products. Or if for next year we didn't get there, I don't know, depending on where you are in the packet. We start to realize, okay, which single atom is going to go with this other atom? Why? Why? They want stability. Why? Valence electrons. Again, it goes back to all I want in science is a full outer shell. You know that song. So again, when bonds start to reform into new combinations, hence the chemical change, hence the chemical reaction, energy is given off. How much? Depends on the combinations being produced. So here we're actually going to do a calculation. These calculations not only need you to have knowledge on how to predict products at times, you also need to have knowledge once again on how, once you get the equation, you can look up values and figure it out, but you also need to figure out how to draw Lewis structures, which we did before. But again, this is another skill where things in previous chapters, these skills build. If you don't focus and master topics in previous units and honors courses, the next chapters become harder. If you're not very skilled with Lewis structures, then you're not going to do well with this. So that's why I always say when you go to the high school, things build. If you struggle in something, make sure you ask your teacher, whoever that would be or will be or is, to help you with it so you get it for the next chapter. That's the key, because everything builds. Okay, so let's do the first example. So we have combustion of methane. It's a combustion reaction, you know that. CH4, gaseous state, plus 2 moles of oxygen gas, diatomic oxygen. Remember Dr. Brinkelhoff. yields carbon dioxide, gas, plus 2 moles of water, steam, gas. So again, these coefficients count as moles. So we know in our head that this is a combustion reaction. Why? Every combustion reaction is a hydrocarbon. Remember, hydrocarbon, 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 hydrocarbon. Boom, combustion, and water is given off every time. Now, first thing you need to do when you do these bond energy calculations, you need to draw these molecules out. So watch this. We have methane. We know carbon is very versatile, 4 valence electrons, stick carbon in the middle. 2, 4, 6, 8, who do we appreciate? Valence, valence, covalence. There's 1, 2, 3, 4 CH bonds, right, that need to be broken, need energy added into them to start this change. Plus diatomic oxygen, 2 moles of it. So we know oxygen is in group 16, it's got 6 valence electrons. At this point, you should know it's a double bond. You know it's nonpolar, it's diatomic, but here's the thing, I have 2 of these. 2 of these. So you got to make sure you draw 2. Like that. 2 nonpolar diatomic molecules. Yields CO2, carbon in the middle. 2 oxygens surrounding it. Right? And then 2 H2O. Like that. Now the reason why I wrote 2 is because I've got 2 moles of water in this reaction. 1 mole of carbon dioxide, 2 moles of diatomic oxygen, 1 mole of methane, CH4. Now, how do you attack this? You take the chart on the back of your paper. Now you know intuitively you're going to have a negative delta H because this is a combustion reaction exothermic. But how do you calculate? So you look on the chart, and some of these charts vary. So I'm going to use our Pogel chart. And you're going to see here that a CH bond is worth 411 kilojoules per mole. So my question to you is, how many CH bonds do you have? 1, 2, 3, 4. So you're going to take 4, distribute that into there, times 411 kilojoules per mole. Plus, on the reactant side, I've got 2 moles of diatomic oxygen. So what I need to do is, I need to take a look at what is the value for double bonded oxygen. 494 kilojoules per mole. Well, how many? I have 1 double bond, 2 double bonds. Why? Because I've got 2 moles of oxygen. So again, distribute that in there, okay? And then over here, hold on guys, I gotta move these over. There. Man, that picture's fun. All right, now watch this. Here's CO2. I've got 1, 2 C double bond O bonds here. Do you see that again? 1 CO combination, 2 CO. So what do I have here? So I look on the chart, it's 2 times, I'll make that red, my old school technology, 745 kilojoules per mole. Here, whoops, plus 2 moles of water. So I've got 1, 2, 3, 4 OH or HO bonds, which would be, each would be 464. So again, 4 bonds in methane of CH. Now if I had 1 mole of oxygen, it would be just 494 if I had 1 mole. But I've got 2 moles in the balanced equation. So I have 2 double bonded oxygens at 494 kilojoules per mole. Over here with carbon dioxide, I have 1 mole of carbon dioxide. 2 C double O bonds. 2 of these. Here's 1, here's 1. Here I've got 2 moles of water. If I had 1 mole of water, it would be 2 times 464. 464, 464, 464, 464. So when you add these, so what you do then is, take these 2 values on the reactant side, add them together. You take those 2 values on the product side, add them together. And what you get on this side, I've got 2,200, and I'm going to bring this up top because of space. So when I add these 2, I've got 2,632 kilojoules per mole on this side. And the formula you see it up top here, subtract the total energy from the bonds being broken minus the total energy of the bonds being formed. The value on this side is 3,346 kilojoules per mole. So now by looking at this, it took 2,632 joules of energy to break these bonds. How much would they need to absorb the form? The opposite. Here to form these combinations, we had to get more energy from the surroundings. And what happened was, look here, these guys over here, to form this was a total of 3,346. So once these form, the delta H, your value is going to be negative 714 kilojoules per mole. That's your delta H. That's an exothermic reaction. So this net reaction is exothermic. More heat was given off to its surroundings. Why? Product formation. To form them, energy is given off. Remember, bonds forming, energy given off. We gave away a lot more energy to the surroundings. Therefore, the net result is exothermic. And if you drew a little sketch, it would be like this. Negative delta H value. Okay? So again, Lewis structure, knowledge of using moles with coefficients, simple math, very easy. Okay, I'm going to do one more. Let's go down to number 3. Switch it up. Here's diatomic hydrogen, gaseous state, plus diatomic chlorine, gaseous state. Yields hydrochloric acid, 2 moles. Again, acid nomenclature. Now this is an easy Lewis structure problem because here, diatomic hydrogen, they want 2 valence electrons in their outer shell. So a review, this shares one with another hydrogen. They form a covalent bond. Here I've got diatomic chlorine, 2 halogens in the halogen family. They each have 7 valence electrons. And it's nonpolar because these poles cancel out. Their difference in electronegativity is 0. So here you have 1 bond here, 1 bond here. 1 mole, 1 mole. Here now, this forms hydrochloric acid. We know hydrochloric acid is a very strong acid. It dissociates, has a high success rate of dissociation in water and forms a lot of hydronium through ionization. But we need to draw out the structure. And again, we know it's a covalent compound, but it dissociates. Here is the bond. 1 shared pair of electrons with the halogen fluorine, 2, 4, 6, and then 1 shared pair here. So again, we're going to need to analyze the HH bond, the Cl-Cl bond, and the bond with HCl. So again, we realize that we got to get these guys to break. That's going to be endothermic process. Now we got to get these guys to form. Again, when we break these, you've got H, H, Cl, Cl. Who do I go with? Where do I go? Once they're broken apart at our peak point, our transition state, where there's mad chaos, we then start to give off energy once they settle down and find a suitable partner. But again, I have all these atoms here. Once it's balanced out, I have 2 moles. So again, you want to draw another like that, because I've got 2 moles of hydrochloric acid. So now when you calculate it, when you look on the chart, this bond right here is a value of 432 kilojoules per mole. Okay? And when these bonds form, its energy is released. It's exothermic process. How much is given off? If I give off less than what I added, then it's an endothermic reaction. If I give off more than what was added, in terms to break these bonds, then it's an exothermic reaction. So a Cl-Cl diatomic chlorine bond is, let me get my chart, no, I don't know these numbers, I gotta look them up myself, is 243 kilojoules per mole. So you would add those together. Again, 1 mole, 1 mole. One bond, one bond. Okay? Microscopically, 1 mole of bonds. 1 mole of bonds. Here I've got 2 moles of bonds. Again, 2 HCl bonds. What's the HCl value going to be? The HCl value is going to be 431 kilojoules per mole. So now the question is this. How do I figure out the overall net result of the reaction? So then let me double check and make sure that, okay, I got room up top. Okay, so now if I take this, if I add these two together, 432 and 243, and for time's sake I might answer key, we have 675 kilojoules per mole absorbed to break these apart, cause mad chaos, get us to the peak of the reaction, along with the activation energy too. So then, to form, we give off, we release a total of 431 kilojoules per mole to form 2 moles of hydrochloric acid. So then we take 675, right, and we want to, using our formula, and go back to the first page, you see it up here, the delta H of the bonds broken minus the delta H of the bonds formed. So if you take this value, 675 kilojoules per mole, and you subtract it from, excuse me, ooh, I had an error, and guess what? What did I forget to do? Take a look at it. What did I forget to do? Take it, pause the video, look at it. And I don't care, I'm not going to edit this out, because I have to focus, and you need to focus. What do I have to do? See it? 431 kilojoules per mole, looking up here, is 1 of these. How many moles do I have? 2. Oh, snap. You see what happened right there? So really it's going to be 2 times 431, and 2 times 431 is, whoops, 862 kilojoules per mole. Yes, I'm the teacher and I made a mistake, and I'm on video. I don't care. You have to focus. I lost my focus for a second. But luckily I know this stuff really well, I know the formula, and I know I prepared, and I know that this is an exothermic reaction. And I'm looking at my information like something's not making sense, because I prepared. So when you prepare, you're always prone to mistakes. But you're prone to fixing them quicker when you can recognize different things. It's all about preparation. There you go, guys. I'm telling you. How you prepare is how you perform. Okay, so anyway, back to this. So we subtract this and this, and our overall value is negative, hope you can see it, 187 kilojoules per mole is the delta H. This would be an exothermic reaction also. So again, to break bonds you add energy. To form bonds, energy is released. Hopefully this helps. I just gave you 2 examples. You guys try the others. Again, knowledge of how to draw Lewis structures is key. You know carbon is central. Things revolve around carbon. We did the, here. If I gave you this, what is C2H2? Well, right off the bat, put carbon in the middle, right? C2, they share. So this carbon has 1, 2, 3, 4 of its own access to a 5th. This carbon, 1, 2, 3, 4 access to a 5th. Okay, hold on one second. Bring another hydrogen. This one of its own access to another. This one's happy. So this carbon has 1, 2, 3, 4, 5, 6. Uh-oh. But watch. Bring another hydrogen over here. See how this works? They share. So now here's my issue, right here. What do you notice? And I think this is what you did on the test. This is what you drew. If you don't know how to draw Lewis structures, look what happens. You're analyzing a C single bond with another carbon, a CH bond and a CH bond. This isn't fully satisfied. This carbon has 2, one of its own access to another one. 2, so 2, 4, 6. Where's my 8? Octet rule. This is fine. This is fine. Look at this, carbon. 2, 4, 6. What do I, oh no. Bring these up here. Now look at it. These then they take their two, and they share and form a triple bond. 2, 4, 6, 8. Who do we appreciate? Valence, valence, covalence. Fulfills the octet rule. Look at this carbon. 2, 4, 6, 8. Who do we appreciate? Valence, valence, yay, valence. So again, by changing this, look how much it changes the problem. So it's a triple bond here. 2 carbons, fully octet rule satisfied. 2, so you would have this. 2 CH bonds, and then a C bond. 2 of these, and 1 of those. And that's how you attack it. Be very careful, please. I'm telling you. Be careful, be focused. Okay. Hopefully that helps. Get to work. Work hard. All right. Again, mad shout out to you people. There in period 3. Very good. There we go. Here. Shall I zoom in on you guys? Here we go. Nah, I can't do that. But yes, very nice. Thank you. All right. Later.